In this video, we're going to be taking a look at the classic bowling ball problem where a bowling ball is slipping along the lane as it's released at 4 meters per second, and we're going to find its final velocity. Now, let's go ahead and draw the forces on this bowling ball. We have the force of gravity, which is mg, and then we also have the normal force pushing up perpendicular from the surface, which is equal and opposite to mg. Now, as the ball is sliding to the right and moving this direction, which we'll call the positive direction, we have a force of kinetic friction that's opposing the slide. Now, with that being said, we have some linear motion and we have some rotational motion as well. So let's focus on the linear or translational motion first. Now, we know that the sum of the forces equals the mass times acceleration according to Newton's second law, and the only horizontal force is our force of friction. So the force of friction is our net force. Now what we can do is do some substitutions. Now we know that the force of friction is mu times normal force, so we're going to take mu times mg, because mg is equivalent to the normal force as mentioned earlier, and that is equal to m times a, and then the mass actually ends up dropping out. Now from there, we're going to do a substitution. So we know that a is equal to the final velocity minus the initial over time. So let's go ahead and rearrange this a bit so that it's set equal to vf. All right, so I did a couple things there. I remembered that I forgot a negative sign over here because our force of friction is opposing the slide to the right, and the right is positive, so that means this force is negative. So I put a negative in front of the mu g. I took this t, multiplied both sides by t, which brought it over here, and then I added vi to both sides. So I basically put the vi right in front, and then now we have our vf equal to vi minus mu gt. Now, secondly, we want to take a look at the rotational values. So instead of forces, we're going to take a look at the torque from friction, and that equal to I times alpha. So taking all of these linear quantities over here, and then changing it to the rotational quantities. Now for torque, that is the force of friction times the lever arm. The force of friction is still mu times normal force. The normal force is still equal to mg. And then now we're going to include that lever arm, which is r, the radius of the bowling ball. Set that equal to 2/5 mr squared, which is the moment of inertia of a sphere, and then put that alpha right over here. So let's go ahead and rearrange this a bit for alpha. One of the r's is going to cancel out, and the m is going to cancel out. And then if we cross multiply the 2/5 over here, it becomes 5/2. We have the mu g over here, and then we're going to divide both sides by this r. Now we're going to do something similar to what we did in the previous part. We are going to do a substitution for the alpha, and the omega final minus the omega initial over time equals our alpha. But initially there is no rotational velocity, but eventually it has some kind of omega final. So if we are solving for the omega final, we just multiply both sides by t. So this will change to 5/2 mu gt once we multiply both sides by t, still divided by r, and that is equal to omega final. Now, what we want to do is we want to combine these formulas together. So we know that v equals r times omega, and omega is all of this over here. So if we just take all of this and slide that in for this omega right here, it's basically just multiplying it by r. So what would happen then eventually is this r would cancel out this r over here. And then this would then be equivalent to the velocity. So the velocity would be equivalent to 5/2 mu gt, and then our r is gone. And then we have our previous setup where it's VI minus mu GT equals VF. So let's go ahead and clear some room and then combine these two together to get our final solution. Now for our final step, we're going to combine these two formulas together to get our final answer of what the final velocity is. So we have 5/2 mu GT, which we got using some of our rotational quantities, and then we got VI minus mu GT using our linear or translational quantities. Now, at a specific point, the rotational velocity, which is basically the tangential velocity of the ball, meets that linear and translational velocity. At that moment, that's when velocity equals r omega, which we used a little bit earlier. And that's the point where the ball stops slipping. So we already used this formula a little bit earlier to get our 5/2 mu GT. And now we can set the 5/2 mu GT equal to VI minus mu GT. Now from there, what we can do is I'm going to go ahead and solve for the time first, actually. And what I'm going to do is add this mu GT to both sides to get this canceled. And when I do that, I get 7/2 as my coefficient in front of the mu GT, and that equals VI. And then if I just rearrange things a bit to isolate for T, then the 7/2 goes over to this side and becomes 2/7 if you cross multiply it. And then we have the VI divided by the mu and the g. And then that would cancel out the 7/2. And then after I divide the mu and the g over to the other side, then I would have isolated the t. So this is going to help me find my t over here. And then if I take 2/7 times VI of 4 meters per second over the mu of 0.1 times 9.8, we get our time of 1.17 seconds. Now after that, if I go ahead and take that time and plug it into either one of these formulas, I would be able to get my VF. So I'm going to go ahead and use this one over here, 5/2 mu GT. So my velocity equals 5/2 mu 0.1, g 9.8, and t 1.17 seconds. And then when I do that, I get a final velocity of it rounds off to 87 meters per second. So after using a bunch of linear and rotational values and then combining them together, doing a ton of cancellations and substitutions, we finally got our time the ball slips for, and then the final velocity that it has. I hope that was helpful to you. Thank you for watching and listening.